So, like I just said, this is joint work with Eric Allender, Josh Crocho, Peter Van Melkebeek, and Chris Moore. So let me start by defining the minimum circuit size problem for you. So this is the computational problem where you're given a string x and a threshold theta, and the question you're supposed to answer is whether or not the circuit complexity of x is at most theta. So there's many different variations on this depending on what exactly circuit size means, but sort of morally all these different things are equivalent. One variation that concerns us today is motivated by this connection between circuits and time-bounded Turing machines with advice. It's called MKTP, or the minimum KT complexity problem. So the idea is you can describe a string x by a program and some advice. And the way this program describes x is on input some index I, the program has to output the ith bit of x. Okay, so then the complexity of this description is the size of the program plus the length of the advice plus a worst case bound on the running time of the program. So then the KT complexity of x is just the complexity of the simplest description of x in this model. And let me just emphasize the program has random access to the advice, so it doesn't have to sort of waste time seeking around to find bits on it. And then also it only provides random access to x, so it doesn't have to sort of pay the cost of writing all the bits down in this running time component. Okay, so that's KT complexity, and so then we can define MKTP to just be like MCSP, but with KT complexity instead of circuit size. And then just like how circuits are equivalent to time-bounded Turing machines with advice, KT complexity is polynomially related to circuit complexity, and so this really is a variant of MCSP. So these problems are common suspects for NP intermediate status. I guess not important enough to be mentioned in Christos's talk, but I don't think most people would agree with that. So some other common suspects he did mention are factoring, discrete log, graph isomorphism, and a really interesting question you can ask here is what kind of reductions exist between these problems. So factoring, discrete log, graph isomorphism, they all have randomized reductions, randomized polynomial time reductions to any MCSP variant. But then depending on the problem, you get different sidedness to the error in these reductions. So factoring a discrete log, they have zero-sided error reductions. Graph isomorphism has only a one-sided error reduction. So having said that, the natural question is, can you get rid of the other side of the error in this reduction for graph isomorphism? Okay, and that's one question we answer here. But before I get into that too much, let me just say that getting rid of a side of error in an algorithm like this really amounts to being able to somehow witness that the answer that you're stating is actually completely correct. So for example, with factoring, getting zero-sided error is real easy because you just kind of sit around and wait until you actually have the factorization. You never output some sort of false factorization or something. It's really easy to check that it's right. And for graph isomorphism, the one side of the error that is taken care of already is the fact that you can witness isomorphism by just waiting until you have an isomorphism. So in order to get rid of the other side of the error in this reduction, you have to somehow witness non-isomorphism. Okay. And one of the limitations to the techniques in this area is that they all kind of focus on using this MCSP variant to just generate witnesses that are ordinary NP witnesses. Okay. On the other hand, we don't actually have sort of NP witnesses for non-isomorphism, at least not at this point in time. So that's really kind of a barrier that we have to break. So having said that, we did actually get past it. And the main thing we did is to use MKTP in the verification process of these witnesses. Okay, so the consequence is this theorem. Graph isomorphism, ZPP reduces to MKTP. And the really critical thing here is being able to witness non-isomorphism with help from this MKTP oracle. Okay. Okay. So the techniques that we have are actually pretty general. There's not really anything specific to graphs in here. So I have some other sort of isomorphism problems that our stuff applies to. You might not think of discrete log as an isomorphism problem, but it kind of fits into our framework, so I can list it here. And the reason for mentioning these is that unlike graph isomorphism, all these problems, the best known algorithms are still pretty far from polynomial. Whereas graph isomorphism we know is not too far away. Okay, so let me sketch you the proof of this. And the really critical thing here is being able to witness non-isomorphism. So let me start with the case of two rigid graphs. So a rigid graph is a graph where when you start with two distinct permutations of the graph, and you apply it to the rigid graph, you get distinct labeled graphs in the end. So all the information about your permutation carries through when you apply it to a rigid graph. Okay. So now, as was mentioned, we kind of use this idea from interactive proofs where we think of picking one of the two graphs at random, applying a random permutation to it, and then sort of realizing that there's a difference between how these distributions behave depending on whether or not the graphs are isomorphic. So specifically, in the isomorphic case, the entropy is about log of n factorial, or exactly log of n factorial. We'll just call this S. Whereas if the graphs are not isomorphic, there's an extra bit of entropy present corresponding to sort of which graph you picked a sample from. Okay, so that's sort of the setup, and the main idea that we have is that you can use the KT complexity of a random sample from this process as a statistic that measures the entropy pretty well enough that you can witness non-isomorphism. The picture is the following. So what happens is the KT complexity of a sample from this process, you can think of it as concentrating around the entropy very tightly, and crucially, it's never much larger. Okay? So then to witness non-isomorphism, we can just sort of slap this threshold in the middle, and just once we get a sample that has KT complexity larger than this threshold theta, that's a proof of non-isomorphism. Okay, so this picture is a small I because it's not the KT complexity of one sample, but rather the sort of amortized KT complexity of a sample over some large polynomial number of them. Okay. So the reason for this is that within one sample, there's information about sort of the permutation you picked, and then which graph you started with. There's also the information of the graph itself. This doesn't contribute to the entropy or anything, but it is still part of the string. So the idea is that basically we can extract this kind of information out and then take a bunch of samples, and what happens is the cost of, say, describing the graph gets amortized out and sort of doesn't matter. Okay, so that's the picture. So let me show you a brief sketch of the proof of how this works. There's two things we have to show. One is in the non-isomorphic case, we have to argue that the entropy is significantly larger than this threshold. This follows from a straightforward counting argument. There's not much more to say there. And then in the isomorphic case, we have to argue that the KT complexity is never much larger than the entropy. So let's do that. So we have the setup where we have two isomorphic graphs, a bunch of samples from that, and we need to encode it somehow. And the specific bound that you get on the KT complexity of the sample is what's up on the slide. And the way to read this is that you have this term TS. This is the entropy that's present in Y. It's sort of the unavoidable cost we have to pay. And then there's this error term that crucially depends sort of significantly sublinearly on T. Okay. So what happens is we can sort of divide the whole thing through by T, and you see that the amortized KT complexity of a sample is bounded by the entropy of a sample plus some error term that we can make arbitrarily small by taking T to be a very large polynomial. Okay? Okay, so a brief sketch of the claim. You start by writing the string Y as a bunch of permutations of just the first graph. The reason for doing this is that it helps to clarify sort of where the entropy really comes into Y. And then we describe each of these permutations in a sort of information theoretically optimal way. Okay? So each permutation requires sort of S bits of entropy to describe. And so we'll spend those S bits doing that, and that gives us the TS bits, or the main term of the bound that we have. And then the rest of what we have to do is sort of convert this encoding into the actual string Y. So the way we'll do that is we'll just store the graph and maybe some extra small parameters in the advice. And then to decode the ith bit of Y, we just have to look up which permutation is relevant, read off the encoding, decode that, apply the permutation to the graph, and then output the right bit of the adjacency matrix. Okay? Okay. So then this shows that the KT complexity of Y is bounded by the TS for bits from point 2, plus this like polynomial and n part from 3 and 4. and then that basically gives the claim. It's a little bit more complicated than that, but that's the main idea. So I think that takes care of the proof of our witness system for non-isomorphism for rigid graphs. So let me show you how to extend this to non-rigid graphs. Things are basically the same as before. The first thing we have to do is sort of tweak our meaning of S. So rather than being log of n factorial as a permutation, or the entropy in a random permutation of a rigid graph, it should now be the entropy in a random permutation of our input graphs, which aren't necessarily rigid. And so it should be like log of n factorial over the number of automorphisms. So then once you change that, everything goes through pretty much unchanged, modulo two complications. So the first one is we have to make sure that we encode each of these samples in an information theoretically optimal way. We need to be very careful about that part. So in particular, if we have a non-rigid graph, we can't afford to encode each permutation of that as like a number between 1 and n factorial. It's too much. We would need to encode each of these things as a number between 1 and sort of n factorial over the number of automorphisms, or how many distinct permutations that there are. So it turns out that you can do that. It's in the appendix of our paper, but in a few slides, I'll mention a sort of much more generic way around this that I think is a little more salient. Okay, so the other complication, let me do that first. So this is that knowing our threshold theta. If you remember the picture, we have to know how many automorphisms there are of our input graphs in order to be able to write it down. So remember, theta is like s plus a half or so. S depends on the number of automorphisms, so it's kind of an inescapable problem. So the way around this is to realize that we don't need to have an exact knowledge of theta all the time. It suffices to have sort of a really good estimate for it that's never too small. And you can see from the picture that this is still going to be the kind of witness system that we want, because in the isomorphic case, the sort of amortized KT complexity is never larger than any estimate for theta, whereas typically the opposite happens in the non-isomorphic case. Okay. So then giving this overestimator for theta is actually equivalent to sort of underestimating the log of the number of automorphisms in a graph. And this is something you can actually do. And the idea for this is you start with a sort of known search to decision reduction for graph isomorphism. And what this is an algorithm which takes an oracle for graph isomorphism and computes the generators for the automorphism group of a graph. So then you plug in a possibly faulty algorithm for the graph isomorphism oracle. Okay, so the critical thing of what we're doing here is witnessing non-isomorphism, and I'm relaxing that constraint, and this actually makes designing such an algorithm much easier. But the end result is that this composition is an algorithm which takes an input, a graph, outputs generators of some subgroup of the automorphism group, which is typically the entire automorphism group. So then some basic computational group theory says you can compute the order of that group that you have. And because it's typically the entire automorphism group and always a subgroup, you always have an underestimate of the number of automorphisms that's typically right. Okay? So that's the underestimator that I promised, and that you can then turn into an overestimator for our threshold theta, and that completes our witness system. Okay. Okay. So earlier I mentioned that there's this kind of generic sense in which you can encode objects in an optimal way. So that's the statement of this lemma here. So the generality is you can, for any circuit C, which you think of as sampling a distribution, for any circuit C which samples a so-called flat distribution, or equivocally a uniform distribution on some subset of possible outputs, you can encode all of the outputs of this circuit by strings of length that are pretty much the entropy of the distribution plus some small error terms that are ultimately irrelevant. So an example of this is for any graph, there's a circuit that samples the permutations of this graph uniformly. This is a flat distribution. So you can encode each of these outputs, the distinct permutations of a graph, but in an essentially information theoretically optimal way. Okay. So the most I can say about the proof is that it uses universal hashing. And I don't know, I guess it's a new way to me, but I mean, I'm pretty young, so maybe it's not new to some of you. Okay. So that's that. Finally, I want to get into sort of the conditions under which our techniques apply. If you were to read through and parse these, and I'm not going to make you do that, you'd see that they're pretty benign. So let me walk you through them for graph isomorphism. So here, this big omega is just a set of labeled graphs, and then the group H is the symmetric group Sn. The first condition says the basic operations like multiplication, inverses, stuff like that are efficiently computable. Of course, we know how to do these for permutations. Condition 2 says the number of permutations is efficiently computable. I think we all know how to do that. And then the third one is that you can sample random permutations. Again, we know how to do this. Condition 4, what it asks for is for you to assign to each permutation some string that somehow identifies that permutation, so the mapping should be injective. But then also, what's important is that the string depends only on kind of the abstract idea of the permutation and not sort of any way the algorithm might be representing it. So you can imagine that H is actually some sort of quotient group, and you only have sort of a representative of a particular coset, and then the point is that the string that you represent things with here needs to depend only on the coset and not the representative. Okay. So in condition 5 is real similar, except instead of assigning a string to permutations, you need to assign strings to labeled graphs that somehow identify the graphs, and of course you can just use the adjacency matrix. Okay. So once you've satisfied those conditions, our techniques can be made to apply, and you get the zero-sided error reduction to MKTP. Okay, so since I have a little more time than I originally planned, let me just mention that there were a couple places where we used a little bit of structure of graph isomorphism in the proof I sketched before. We use this like search to decision capability that it has that doesn't hold for general isomorphism problems, but we do have some ways in our paper that kind of work around this issue. Okay, so that's that. Oh, right, corollaries. So those three of the problems that I mentioned before, these are new results that our theorem applies to. So they all have zero-sided error reductions to MKTP as well. So for instance, you don't think our result is as interesting for graph isomorphism, but you think one of these is interesting, then I guess that helps. Okay, so finally some open problems. So our techniques only apply to MKTP, or at least sort of formally everything goes through only for MKTP. They sort of work 99% of the way for any MCSP variant. An interesting question is whether or not you can close this gap. The other question is to what extent our techniques apply to understanding statistical zero knowledge. So sort of one of the takeaways you should get from this is that you can estimate the entropy of a distribution by this sort of amortized KT complexity measure. And since statistical zero knowledge is all about sort of understanding the entropy of distributions, you would think that our techniques should apply there. And indeed, they sort of mostly work. So if you want to get these kind of zero-sided error reduction, you need a sort of kind of worst-case sense of flatness to apply our techniques. But with statistical zero knowledge, the best tools we have only let us get a sort of kind of average case sense of flatness, and the gap between those is too much. But, okay, that's all I'll say there. So let me just recap. Again, the main takeaway here is that you can use the KT complexity, or this amortized KT complexity, as a measure of the entropy of a distribution. And then we showed how to use this to witness non-isomorphism of graphs, but then also other objects. And okay. So that's that. Let me say thanks for having me. And then if there are any questions, I can try to take care of them now. Yeah, we do. Yeah, and you can get one. So this was originally approved a few years ago through some other techniques. You can get it from ours too. And really the hard part is getting this kind of zero-sided error thing. Yeah. Okay.
So I understand right that the main benefit of this MKTP over MCSP for your result is this kind of sort of local access to the advice that you don't need to spend
Yeah.
additional time to read the entire
Yeah, so that's kind of it. So you can sort of simulate that behavior in circuits too. But the way you have to do it is you sort of have to say, okay, this is my advice string, and now I need to come up with a circuit that provides random access to it, and the circuit needs to be like as small as possible. So like I said, our techniques kind of get you 99% of the way to MCSP. But the sort of the one little technical piece that we're missing is that for KT complexity, we have sort of a very precise knowledge of the complexity of a random string. But for circuit complexity, we don't actually have a precise enough understanding of this. And it's basically, if I show this slide, or rather this slide, you would need to take t to be sort of exponentially large in order for our current knowledge to give this picture exactly. Okay.